So in this video, we'll be looking at standard forms. It's an important concept in linear programming. So first, let's slowly look at what are the topics and the main headings that we'll be looking at in this tutorial. So first, we'll be looking at what standard forms are, as in general definition and general understanding. Then a procedure to understand and convert problems to standard forms. After understanding these, we look at a sample problem which is solved, and then we look at a practice problem and see what to do to get the required standard form. So first, let's look at how we know, like, if a set of constraints in a problem are actually in standard form or not. Like, what are the conditions? First is all the constraints should be equations. So here you can see an example: maximize z equal to 4x1 plus 3x2, and we have some constraints. You can see that all of them have the equal to sign, which implies that they're equations. Secondly, all variables should be non-negative. So x1, x2, s1, s2 greater than or equal to 0, non-negative constraint. You can see the greater than or equal to sign there. Now, as we said, the second thing we'll be looking at in this video is the procedure to convert a certain problem with a set of constraints into standard form. So first we need to identify if it is a case of slack or excess. We will see what they are shortly. Next, we'll have to add or subtract the slack or excess variables like respectively. So basically, if it's a case of slack or excess, we'll have to add or subtract. Third, we'll have to convert all equations so that there is an equal to sign. Like, nothing should have greater than or equal to or less than or equal to. Everything should have only an equal to sign. Finally, we need to add the new slack and excess variables after conversion, that is, to the constraints. Now, let us try and visualize the case of slack and excess. So, the general representation for any less than or equal to LPP constraint is x1 till xm is less than or equal to n. So, x1 plus x2 plus so on till xm is represented by these violet lines, and that is less than or equal to some value n. So, n can be this whole rectangle. That means this blue portion is what the violet portion is falling short of to become n. So we can call that extra portion as S1. So what we can do is add this S1 so that now the entire thing becomes equal to n. And now we can convert it to an equal to sign. Now we'll see the case of greater than or equal to. Here we call it as a case of excess. So the representation is x1 plus x2 plus so on plus xm is greater than or equal to n. Now here what we can say is that the total portion is x1 plus x2 plus so on till xm. That is the violet and the blue portions together. The violet portion, so you can see the whole thing is x1 till xm. The violet portion represents n. That means this whole thing is exceeding n by some portion represented by the blue portion. That we can call as S1, and we need to subtract that extra blue S1 quantity, so that now we can say that it is equal to n. So we are subtracting it some quantity S1, so that now this entire equation becomes equal to n. So now we are able to eliminate greater than or equal to and introduce the equal to sign. So now that we've clearly understood what these things are, let us take a sample problem and see what we need to do. The problem is we need to maximize z is 20x1 plus 15x2, and we have some constraints: x1 less than or equal to 100, x2 less than or equal to 100, 50x1 plus 35x2 less than or equal to 6000, 20x1 plus 15x2 greater than or equal to 2000, and x1 comma x2 greater than or equal to 0, which is the greater than or equal to constraint. The other are regular constraints that are present in the problem, and we can see the first three are less than or equal to, and the third is a greater than or equal to. So in the cases of the first three, we add a slack variable. Third, we subtract the excess variable. So now we need to introduce this S1, S2, S3 and E4 in the last greater than or equal to thing, and say that we've converted.